Hello everyone and welcome back to the discussion about the graph of trigonometric functions. So here, last time we introduced two trigonometric functions that we're going to learn how to graph them before we learn the other graph of trigonometric functions. So these two trigonometric functions that we're going to learn on how to graph them are sine function and cosine function. So you see this animation. By the way, just to remind you, this animation is not mine. In fact, it exists in any internet browsers. Just search it here. Wait, hold on. Let me see the full name of this animation. Just search this in your Google Chrome, like sine and cosine animation from unit circle, and it exists as a Desmos link. So there you can experiment that graph the same way how I did it here. All right. So credits to the owner for making this animation. So let's continue. All right. Now what we're going to do is we're going to talk about the graph of sine. All right. So here, let me just wait, no, sorry, but this is wrong. Let me just make the graph of the cosine invisible. All right. There we go. Okay. So you see pink, this pink curve right there? You see that? That is the graph of the sine function. So with that, in here, in this video, we're going to learn its concepts and the overview of the graph of sine function. Actually, this is the, you know, the overview of the sine function. Don't get me wrong, because I already showed to you what does the graph of sine function will look like, right? However, you see, later on, I'll show to you that I have a given sine function, but the way how it looks like in terms of its graph is somewhat similar to the graph that I showed to you here, or the animation here, right? In which I will show it to you later. For now, let's talk about the concepts or other information that we're going to learn about the graph of sine function. Right? So let's go to the next presentation, which is here. Right? Okay, let me just erase the writing. Right? And let me just rewrite these again. Right? Right. So sine function. The graph of sine function. The graph of sine function is also known as a sine curve. All right. Now, here's the thing. Let us learn the properties of sine function. To be particular, when your sine function look like this, look like this. If your function, to be particular, sine function look like this, sine x, this is actually your original function. Okay? And the graph of it would look like this. It would look like this. All right? This one. Let me just, there you go. This one, okay? That's a graph of sine x. In fact, that is actually a graph of the animation, the one I showed to you earlier. Okay, remember the animation in the like few first minute or second, of me introducing you guys or introducing the topic of this video. Yeah, that's basically the graph of sine x. So, okay, we have the graph of sine x. So, what are the properties of it? All right. First and foremost, the domain is set of all real numbers. So, what does it mean? Well, if you're going to explain it, algebraically speaking, it means that assume that we have this this equation, right? Y is equal to sine x. This equation, y is equal to sine x, this is just basically the same as writing it as f of x is equal to sine x, right? So here, if your domain is set of all real numbers, it implies that you can substitute any values for your x. Like for example, I will substitute pi or pi to the x. So if my input is pi, that means I have sine pi as a result. In fact, sine pi is basically zero. Sine pi is basically zero, right? So not only pi that you can use to substitute it in the sine function, but also other values. So point being, you can substitute any x values to the function. So that's the domain. Now, I can explain it. Sorry, let me just trying to explain it again carefully. Um, going back, what was it again? I can explain it to you visually. Or like, how would you know that the domain of the sin x is in fact set of all real numbers, right? Let me again switch the presentation here. Okay. So I'm going to use the graph that I actually made. Let me just pause this one. Wait, hold on. Let me just say I can pause here. Wait. There we go. Let me just use this one. Okay. So this is basically the link of the Desmas I made to illustrate the graph of sine function. So you see this? This is the graph of sine x, by the way. Okay. So look at this one. Okay. I want you to relate the curve, a flow of the curve to the x-axis, which is basically the white horizontal line, the one you see, the one here, this one, right? This one. Okay. So here's the thing. Follow the curve. Let's from the origin or the center of the graph, right? Or middle of the graph. Then follow the curve, right? What did you observe? Well, first things first, the pattern repeats, from starting here, up, down, up, down, up. Yeah, a pattern repeats. But that's not actually, I mean, yes, it is actually one of the important observations, by the way. But there's actually another main point here. Because if you're going to take a look, the graph goes on forever and ever and ever and ever. Okay? Let me just say I'm gonna stop until I reach 100. Where is it? Oh, here, 100. And you see, even if I reach until 100, beyond 100, the graph still exists. Right? So what does it mean? It means that from center going to the right, the graph goes infinitely. Okay? So that means, in this case, okay, from the middle to the right, it implies that the domain is basically from the center going infinity. Right? From center going infinity. Why is it going infinity? Because the graph goes on and on forever. Now, how about we do the same thing like from the center going to the left, like here. From center, then going to the left. Okay, again, relate the x-axis and the curve itself, or the flow of the curve. So I'll start here, then I'm gonna move to the left. Now look what happened. It still goes on forever and forever. So the same implication as well. Like if you're going to start from the center and go to the left forever and ever, if you're going to take a look, the graph goes on forever and forever. So that means the domain at that part from center to the left is basically from center going to negative infinity. There's no limit, right? Now combine them both together. Like the no, what do you call this one? The domain from center to the left, the domain from the center to the right. Combine them together and let's take a look. Okay, from negative infinity, like starting from negative, it goes forever and ever. And if we go to the right, on and on, forever and forever, it still goes on forever and forever. You know what I mean? So what does it imply? It implies that the domain, since the graph goes on forever, that means the domain also goes on forever. So from negative infinity, center, positive infinity. So negative infinity, positive infinity. In other words, the domain is set of all real numbers. Okay? Because it goes on forever and forever. All right. So that's how you explain the domain of a certain graph of a function. But let's talk about the other part of it, which is the range. Okay, the range of sin x. According here, the range of sin x is from -1 up to 1. Okay, exclusively speaking, meaning -1 and 1 is included. So what does it mean? It means that if you're going to get the result of a sine function after you substitute with any x value, expect that your answer is within this interval. All right. So let me give you for example. Let's just say I have what do you call this one? Uh, let's just say what's a better suggestion? Let's just say I have 2 pi, right? 2 pi. Okay. So 2 pi. Substitute 2 pi in the sign. What will happen? I will get 0. All right. How about any number? Like assume that they are in radians. All right. Because if you're going to substitute a value on the x of sine function or any trigonometric function, they should be either in radians or in degrees. Right. So since I'm going to substitute any number, so I assume that this should be in radians. So for example, I have 3/4, right? 3/4. So if I'm going to substitute 3/4 here, let me just open my calculator for a second. All right. Hold on. I can't. Somehow I can. Hmm, wait. For some reason I can't though. Huh. Wait. Give me a second. All right. I'm trying to change my calculator into radian. Huh. Wait. For a second. Hmm. Where did I? Where did I change it? Actually wasting time here. Hmm. You know what? Let me just wait. How long is my recording? Hmm. Right, hold on. Maybe this one will do. Wait. Sine, then. Oh, yeah. Finally. Sine 3/4. Alright. So basically, sine 3/4 is uh approximately at two decimal places 0.68. Alright. So let's just say we take sine of 100, 100 radians. Right? That's actually very big, but it's just a experiment to just show to you. Right? So here we will have -0.51 approximately. Right? So you see, no matter how big my number is, whether if it's in degrees or in radians, the result would be what? According or basing it to this interval. Okay? Its result could be between -1 to 1 exclusively speaking. All right. Now, how about I explain it to you graphically? Like since I explained about domain, how about its range? Okay. I'll show it to you. This one. Now take a look at the graph of sin x. Look at this one. Okay. So for the domain, right, we're going to relate the curve and the horizontal axis, which is the x-axis. Now, what we're going to do is we're going to do similarly. I mean, to do it similarly, but instead of relating the curve to the horizontal axis, we're going to relate it to the y-axis, which is the vertical. Now, look at closely. Okay, the curve goes up here, which is exactly at 1 unit upward, right? Then we go down. Okay, we go down. And here, when we go down, it reaches to -1, right? It reaches to -1 here, this one. Now we will do it again. We go up, right? It still what? Stops at exactly 1, right? And when we go down, right, which is here, it stops at -1. So what did you observe here, right? What can we observe from it? Wait, hold on. There we go. It stops at -1. So what can we observe here? Well, not only that the pattern repeats, but you see the curve is restricted in a way that they should only reach the maximum height of 1 and the minimum height of -1. So there's like a restriction or the boundary where the graph should only go up, okay, like until what part the graph will go up and until at what part of the graph will go down. You get me? So here, it seems like the maximum height is, or the maximum point that the graph will achieve when your graph is sine x is 1. Then, when you go down, the minimum point where the graph should be going down is -1. So meaning after you reach -1, you'll go up again. And once you reach 1, you'll go down again. So there is a restriction or the boundary. So that means your range is between -1 and 1 exclusively. Right? Wait. No, 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 wait. Oh, wait. Wait, sorry. Um, Forgive me. When I say exclusive, it means that -1 and 1 is not included. Forgive me. I meant inclusively. I'm so sorry, guys. It's inclusive, okay? Not exclusive, inclusive. When I say inclusive, that means not only numbers between -1 and 1 are included, but so are -1 and 1. Because when you say exclusive, that means 1 and -1 are not included, but between them, they are included, right? So forgive me. Okay, I'm so sorry. So again, from -1 to 1, inclusively speaking, that is the range of sin x. Alright, we good? Alright, we good. Forgive me for the mistake. I'm so sorry. Alright, let's go back. So here, now I told you about the range. Now let's talk about the period. Now, you see, period is basically what? Where it's basically responsible on repeating the pattern. Alright? So here, the graph of sine function, where the sine function is sine x, your period is 2 pi. Okay? Your period is 2 pi. So what does it mean? So in the graph of sine x, your period is 2 pi. It implies that in every length of 2 pi units actually, to be particular, 2 pi units, the pattern repeats. Okay? The pattern repeats. So just like here, you see this? This is 0, right? This is 0. And once you reach at the corner, this corner right here, this is actually 2 pi, all right? Exactly 2 pi. This point uh where it uh let's just say touches to the x-axis here, that is 2 pi. So from here to there, if we're going to get the length from the starting point to the end point, you will have a total of 2 pi units. Okay, that's the total length. Now, after that, what happens? Like after you reach, like from here to there, to you reach 2 pi units, what happens? The pattern repeats again, right? It repeats again. Like, let me show you again the graph, right? Hold on. Let me show you the graph again. This one, all right? So you see, this one, wait, yeah, okay. You see this one by 0. Now, if you're going to take a look, okay, this is 2 pi, right? 2 pi. So from 0 to 2 pi, if we're going to get the length, okay, that's 2 pi units long. Now, after you reach 2 pi, now take a look. The pattern repeats. So from here, you stop right here. Then you're going to go up again and go down. Then you're going to stop right here again, by again. So, meaning, when you reach a length of 2 pi, okay, the pattern repeats, which makes sense, all right? 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 This is the 2 pi. Then we go for another round. The pattern repeats in here at this second pattern. You stop until 4 pi. Now get the distance between the two. 4 pi minus 2 pi is still 2 pi units. You get me? So this is the period of sine x. This is the moment where the graph will continue, will repeat the pattern once you have 2 pi units in length. And speaking of repeating the pattern, I am also implying that, uh, what, 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 I'm also implying that you also have one complete cycle, right? In every length of 2 pi, the pattern repeats, the one I showed to you. Hence, you have one complete cycle when the length is 2 pi, alright? So once, when you have sine x, okay? This is sine x, alright? So in this graph, sine x, once you reach the length of 2 pi, that's already one complete cycle, alright? So one complete cycle is basically 2 pi. Another thing to know is that sine is basically an odd function, right? When you say odd function, basically like if you have f of x, right? Then let's just say in here you substitute your input as negative x, all right? Once you substitute your negative x to the function, and then the result is negative f of x, or it's negative overall, that means it's an odd function, which makes sense actually, because you see, sine of negative x is just the same as negative sine x, right? Try to experiment, like let's just say I'm going to substitute something on the x. Let's just say negative 30 degrees, okay? Then same thing, okay? To the x, it's 30 degrees instead, all right? Instead of negative 30 degrees. So what is sine of negative 30 degrees? When you say negative 30 degrees, that's basically the same as 330 degrees, all right? So that means sine of 330 degrees or sine of negative 30 degrees, that's basically one half, okay? That's basically one, negative one half, all right? Wait, am I right? Is it that way? Really? Wait, hold on. Then let me check, all right? Let me just use my calculator, all right? I forgive me. I illegally. So sine of 30 degrees. Okay. Wait, let me just put a negative sign. There we go. It is actually in fact negative one half, right? I was wrong. Then wait a minute. Negative 30 degrees plus 360. That's basically. Oh yeah, actually I'm correct. Okay, my reasoning is correct. So yeah, it's negative one half. Then here, negative sine 30 degrees. So substitute sine 30 degrees. It's basically one half. So negative times one half, negative one half. So they're in fact the same. So hence, sine x is in fact a what? Odd function. Alright? So yeah, that's basically it. Right? So yeah, that's it. Forgive me if I take a long time to just to just calculate this. Anyway, let's continue. So here in one cycle, it has what? I suppose this graph right here. This graph shows you already that this is one cycle. Okay, this graph. It shows you one complete cycle of it. So here in one cycle, you have what? Number one, the maximum point, which is basically the the peak, like the peak of the mountain. Okay. So basically it's here. This is the maximum point. Then next we have one minimum point. So basically it's like the peak of the mountain but in reverse. So here, right, this is here. the minimum point. Then here we have three x-intercepts, basically the curve where it passes through the x-axis. So first it passes through here, the center, okay, then here, and then here. Okay, there you go. That's it. So there exists three x-intercepts. One, two, and three. Okay. Then lastly, we have one y-intercept. So it has only y-intercept because the graph passes through the vertical axis at this point. Okay, this is your y-intercept. That's the only part where the sine would pass through. My sine x would pass through. All right. So that's it. Now let us know the parts of sine function. Actually, the one I mentioned here, the maximum point, minimum point, x-intercept. Yeah, that's also. I mean, these are also parts of sine function, right? So let me recall them again. So again, the peak here, this is what? The maximum point, right? This one, this is your minimum point, right? Then the x-intercepts are here, okay, this one. These are your x-intercepts. Remember, when you say x-intercept, these are the points where the curve passes through the x-axis. So there we go. X-intercept here, x-intercept there, and x-intercept here. That's it. And lastly, we have y-intercept, which is basically similar as x-intercept, where the line passes through, where the curve passes through where? Y-axis instead, not on x-axis. So here, the 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 graph where where the sine passes through is here. Okay, right? Vertically speaking, this is your y-intercept. So again, maybe I'm being talking a lot or explaining a lot, or keep it in too detailed. Basically, y-intercept is the curve where it passes through at where it passes through y-axis. So on the y-axis, the curve only passes through here. Okay, so there are other parts actually. There are other parts. Well, and what are those? Okay, so one, we have this what you called amplitude. What is amplitude, by the way? When you say amplitude, it's basically the distance between the middle part of the graph up to the maximum point or the minimum point. So you see, right? This is like the middle part of the graph, right? You see this one, this blue line that I just drew here. This is like the middle part of the graph. Now, let's just say that you want to know the distance between the maximum up to the minimum. Not minimum, sorry. Maximum to the middle part of the line. Middle part of the line. Middle part of the graph. So the distance between the maximum point and the middle part of the graph, that is basically your amplitude. Let me just put a amplitude. And that's also the same thing if you want to find the distance between the minimum point up to the middle part of the graph. That is also, in fact, an amplitude. In fact, this is very important in graphing. So you need to know what's amplitude. All right? So what's next? Aside from amplitude, I think there's another thing. We have midline, I'm correct. Is this a midline? Okay. Let me just search it here. All right. Exist a midline? All right. Midline. Uh, hold on. Oh, okay. Yeah, there exists a midline. So the one that I draw here, like this one, right? This one here. Yeah, it is what you call midline. So I'm correct. This is the midline, right? That horizontal line that I just drew here that shows the middle part of the sine graph, that is the midline. So yes, these are the parts of trigonometric functions, all right? But you see, there's one thing that I would like to also include here, right? There's one thing that I would like to include in this parts of trigonometric function. Okay, so first, you should be familiar with these, okay? If yeah, you should be familiar with these parts, right? Because I'm going to erase them. So again, maximum point is basically the peak, okay, on the top. Minimum point, the peak, but below. The middle line, the one, the blue line that I just drew, that shows the middle part of the sine graph. That's the midline. Then amplitude, it tells you the distance between the maximum point and a midline. And likewise, it also tells you the distance between the minimum point to the midline. All right. And of course, we will don't forget to include the x-intercepts and y-intercepts. All right. Let me erase them because there's one part that you need to know too. Right. So let me erase them. Another part that you need to know is what? This part will tell you how would your sine function would look like in terms of its curve. And that is your key points. The key points divides the period by four parts. Now, what are the key points? Here are the key points, all right? The first key point is basically here, this one, okay? The first part is a key point, like the starting of the graph. That's the first key point. The second key point is the maximum point, okay? This one. This is the second key point, right? The third key point is the x-intercept where the graph goes downward. This one. Alright, this is the third key point. Alright? Then we have the fourth key point, which is actually the minimum point. Right? The fourth key point. And lastly, the fifth key point. The fifth key point tells you the end of the cycle. Alright? And as you can see, it really does divide the graph into four parts. Alright? So let me just draw a dotted vertical line here. Wait, let me pick this one. All right, this one and this one. All right, see? So we have the first part, second part, third part, and fourth part. So yes, it divides the graph into four parts. Okay. So now here's the question. Okay, we know the amplitude, x-intercepts, maximum, minimum points. Okay, we know them. But how are we going to know these key points? How are we going to know it? How are we going to know how to find these so-called five key points that will divide the graph into four parts. Yeah, into four parts. How are we going to know that? You will know it. You will know it. By what? By knowing your period. Okay. By knowing your period. Okay. The period will tell you your key points. So for example, okay, suppose we have a function of sine x. And we know that the function sin x has a period of 2 pi. So what does it mean? Okay. Okay. So if I have a period of 2 pi, that means that if I'm going to divide it by 4, I will have pi all over 2 as a result. So that means you're going to use this pi all over 2 to find your key points. All right. So let me give an example. Right? Let me give an example. Let's just say that I have this one. Right? Do you remember this? This graph, the first part of the graph of trigonometric functions. Do you remember? Right? Where I introduced the graph of sine and cosine function and how to graph them by tabular method like this. Like we have a table that consists of two columns, the x and the f of x. Let's try that, okay? So let's have a recall. Let's just say the angles are in 0 degrees. Okay. Now I have pi all over 2, right? Right? Remember, you're going to use pi all over 2 to know your key points, right? Now let's convert this into degrees. Okay. Pi all over 2 is just the same as 90 degrees. All right. So here's what we're going to do. Okay? First, we will start at the very beginning, okay, of the curve, which is basically at the center. So since we started at what was one, we started at the center. That means that it is 0 degrees, right? Substitute 0 degrees to the sine. What will happen? Sine of 0 degrees. What is the result? The result of having a sine of 0 degrees will give you what? Zero. Okay, zero. That means your y is here. So that is your what? First key point. That is your first key point here. You see that red dot? That's your first key point. Now, what's your next key point? Now, right, you start at 0 degrees, right? Now you're going to add it with 90 degrees. Okay, so plus 90 degrees. So you have 90 degrees. Okay, so you will substitute 90 degrees in where? In here. Okay, so sine of 90 degrees. What is the result? So this is 1. So 1 is located here at this point. So again, pi all over 2 is just the same as 90 degrees. So it's here. Alright, this is the second key point. Oh, what's the third key point? So here, right, we have 90 degrees as a second key point. We will add it again by 90 degrees. So 90 degrees plus 90 degrees, you will get 180 degrees. And whatever the result you have, you're going to substitute it to the sine. So you have sine of 180 degrees. So substitute it, what's the result? 0. So here, pi is the same as 180 degrees. So here, since substituting 180 degrees for pi radians will give you 0, so that means it's here. Okay? It's here. And that is your third key point. Now for the fourth key point, what to do? The same pattern, all right? You have 180 degrees. We will add it by 90 degrees again. So 180 degrees plus 90 degrees. So you will have 270 degrees. So substitute 270 degrees to the sine function. What will you get? What will you get? You will get negative 1. So here, sine 270 degrees is just the same as 3 pi all over 2. So it's located here. And since it's negative 1, that means that the the fourth key point is actually here. Okay? And lastly, right, because we need 5 key points. So to find the fifth key point, the same thing. Add the previous number by 90 degrees. So 270 plus 90 degrees, you will have 360 degrees. So sine of 360 degrees is basically 0. 360 degrees is just the same as 2 pi, so it's located here, right? And the fact that it's 0, that means the the point is actually here. This is the fifth key point, right? Which makes sense because in here we have, you see, the maximum point as what? The second key point, the fourth key point as as what? The minimum point, and then these three, the first, third, and the fifth, these are just, these are just the x-intercepts. But you get my point, right? This is how you find the key points. So here, the sine x, the graph of sine x, which is this one, by the way, this is uh, these are the 5 key points when your graph is sine x. Okay, so that's actually the overview because in fact, what I just did here, that is actually the same way on how we are going to do on the next video. All right, because on the next video, I'm going to teach you guys how to graph a given sine function. And speaking of that, okay, give the graph of sine function. Let me show you something very important. All right, so you see, right? I have sine x, but remember what I told you earlier? I said that, you see, yes, we have sine x, but there are actually different types of sine function. And what I mean by types, I don't mean like there's like specific part of it. Like, okay, we have this type, second type, third type. No, what I mean by that is that they're actually they're actually sine functions, but they're actually different or somewhat similar at least to this graph, okay, to this graph here. All right. So with that, we will learn about the graph of y is equal to a times sine of bx plus c plus d. All right. We need to learn this one. And why again? Because this will tell you how different this sine function to the original function. Because we know how sin x would look like, right? We know how sin x would look like. But what if there exists a coefficient to the sine? What if there exists a coefficient for the x? Or, I mean, yeah, there exists as a coefficient to the x, but not only that, but it also has a number. Like, for example, right, we have a coefficient for x, which is 2, you know? Now, what I mean by coefficient, by the way, I don't mean coefficient as 1, but aside from 1. You get me? So basically, there exists a number. All right. So again, going back, what if we have sine of 2x minus 1? So what does it mean? Right? What does it mean when we have sine of x minus 1? Right? Also, what if we have a constant term outside, like for example, 1? So this one, it is still a sine function. Okay? It is still a sine function, but in terms of graphing it, it would be at most or at least somewhat different to the original function. So here, there's like a lot of observations that I'm going to write here, that I'm going to show to you here. But let me give you a visual presentation so that you'll understand what I mean. Okay. So let me just switch my presentation into this. Wait, no, 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 no. Where was it? Here, right? No, not this one. But sorry, that's basically my being. Where was it? Is it here? Oh yeah, right here, right here. So this one. All right. So yeah, right, this one. Right, this is the graph of sine x, right? Now let's just say I have this one. Okay, I have this one. The graph of a of sine of a sine of bx plus c plus d. All right. Let me just copy this. Right. Wait, hold on. Okay. So okay, this is what it looks like if your original function is sine x. Oh wait, no, sorry. This is what it looks like if you mean original sine function, which is like this, the one I just showed to you earlier. Now, let's have an experiment. Let's focus on letter A, right? A is basically the coefficient of sine, right? So here, if your A is 1, obviously there's no changes to the original function, which is this one, which is the same. But what if I increase it? Like, let's just say I have this one, all right? This one. I increase it. See? From 1 to 1.5 to 1.6, let's make it even bigger, 2.8. Compare it to the original one. You see? What happens there is that if I increase the value of A, it seems like it's increasing. You know what I mean? But what if we do it in reverse way? Like we do this, right? This and this. Okay, if we do this, what happens? Not only that it will, it will shrink, but then it will also increase the the graph of the sign in a reverse way, just like this, all right? Just like this, okay? Just like this, okay? So now you see what will happen if you're going to play with letter A. Okay? So if you increase the value of A, it will increase. Okay? If your starting point is 1, but if you do it in reverse way, okay, like for example, you start at 1, then you do it reverse way, it will decrease Then, once you keep on decreasing it, the what do you call it? The height of the curve will increase, but in reverse way, just like this, right? So that's for the A. Now, how about for B, which is basically the coefficient of X? So B here, let's just say your B is 1. So it's just the same as the original function. It looks like that. But if I'm going to increase it, increase the B value, look at that. It shrinks. So if you increase the value of B, it shrinks and shrinks and shrinks even more. If you, of course, if you keep increasing it. But, but if we, what goes on, if we decrease it, so here it will become what? It's stretching. All right. So if your starting point is one, you see this one, the one, right? So if you're going to decrease it, it stretches, and stretches. All right. But once you reach your value of b as 0, it will look like horizontal line, right? Just like how your a would be if, oh wait, sorry. Just like how your a would be, but it's 0. It's a horizontal line. But yeah, going back, okay, that's it. Now, here's the thing. Okay, your b is 0. Now, if you're going to decrease it even more, it will go back, um, it will go back shrinking it, but in reverse way. Okay, in reverse way. Alright? Now you see the difference? If your starting point is 1 and then you're going to increase it, it will shrink, 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 and shrink. Okay? But if you start from 1, then you decrease it and it approaches to 0, it will look like this. Like this. It will stretch and stretch. Then once you reach to 0, it's just a horizontal line. But if you keep on decreasing it even further, in which it will go back, stretching it, but in reverse way. Right? It will look like this. Right? That's it. Right? See? Now let's go to the C. Alright, C is just basically a partner for BX. Alright? Now assume that your A is 1, your B is 1, so what will be your C? So if your C is 0, then it's just the same as the original function, right? But how about we increase it? We increase the value of C, so we will have this. Now take a look. The more I increase it, what happens? The more it will move to the left, you know? It seems contradicting because if it's positive, it should be going to the right? But yeah, here, if your C is positive and you increase it, the graph will move to the left, right? Now, what if, okay, uh, you start from 0, then the value of C is decreasing, like from 0 going negative. It will look like this. So it goes in reverse way. So therefore, the graph will go from the center to the right. All right. So now you see it. Now, lastly, how about the letter D? Letter D is basically tells you where would be the starting point of your graph, right? Uh, I mean, yes, starting point, but vertically speaking. So right, D is 0. But now here's the thing. I will increase the value of D. What happens? It goes upward. But if I would start from 0, then go it to the negative infinity, like, decreasing it, it will go downward. So now you know, right? Now you know. All right. So let's try to have some fun experiment. Like, what if your A is 2, your B is -1, your C is 3, then your D is -1, just like for B. This is the graph. You see? So this is what will happen if your sine function is, yeah, it's not sine x. Rather, it's basically a different type of sine function. So in that, we will learn on how to graph them. All right? So let's try to summarize what we have observed so far. Okay, so let me just switch the presentation. Hold on, let me just switch the presentation here. Okay, so in your A, that's your amplitude, by the way. Your A is your amplitude. Okay, so if you increase the amplitude, then the graph stretches vertically and vice versa. All right, and I think you've already seen how it looks like, right? Like if you're going to increase it, positively speaking, it will stretch. But if you're if you're going to stretch your A, like uh A is, let's just say, between 0 to 1, you know that it's not going to stretch. You know what I mean? Rather, it's going to shrink, right? If you see it. Now, if it goes beyond, like, let's just say A is less than 0, it will go back again stretching, right? It stretches, but in opposite way or reversely. Right? Reversely. Right? I forgot to add the information here. Right? Don't forget this one. Right? And of course, if actually yeah, here. Yeah, actually yeah, that's it. Also, if your A is 0, you will have a horizontal line, right? If your A is 0, then it will be a straight horizontal line. Also, if you put a negative sign on the amplitude, then the graph will flip vertically. Like from that, this is the original, and see what happened. Flips vertically. Which explains why if you're going to decrease the value of A, negatively speaking, it stretches, but reversely or oppositely. Okay? Now, for your B, which is basically Bx, if B is not equal to 1, then the period is not 2 pi. Alright? It will not be 2 pi. In fact, you will have a horizontal line, if I'm correct. Right? Just like for the A. Okay? So, going back, if you increase the value of B, the graph will shrink horizontally, right? Just like this one, right? From this to this, all right? And again, I forgot to, yeah, good. And again, if your B is negative, the graph will flip horizontally. And once your B is decreased by less than 0, it will what? Shrink, or it will shrink horizontally, horizontally, but but reversely. Okay, just like for the A, right? Reversely. That's it. Then for C, okay, which is basically the partner of BX. So here, if you increase the value of C, it will move to the left. Okay, it's left, right? It's left, not right. Okay, it's left. And vice versa. Okay. And if your value of C is not negative or positive, it's just 0, then the graph will not move horizontally. All right. Then lastly, for D, okay, wait, oh, wala, wait, let me just put this thing down. Wait, hold on, hold on. This one, this, wait, this one, this, wait. Oh, like, all right, never mind. I'm just gonna put it down manually, one by one. Right, that's it. Okay, so if you increase the D value, the graph will move upward, right, from here to there, and vice versa. So that means if it goes, if it decreases to D, if it decreases in a way that you will have a negative value, the graph will go down. All right. And if your D is 0, then the graph will not move vertically. If your D is 0, then the graph will not move vertically. Okay. So now I basically summarize the observation. All right. So we're done for this video. I'm sorry if it took like almost 55 minutes video because I want you to understand what sine graph is, right? But the point here is that I hope you understood it, despite that I explain it in detail too much, right? So next video, we're going to learn how to graph a sine curve, right? By the way, you see this, right? I might change something here if ever looks like I'm missing step that we're going to do in graphing the sine, but here's the overview, all right? All right, so that is all for this video. I would like also to what goes one to apologize if this is the re-upload because actually I made a mistake in terms of this one, this part here. I mentioned that it will move to the right, right? I mentioned that, I think. So because of that, I decided to fix it again. By how though? By, yeah, fixing the, I mean, by recording again overall, right? Like from the beginning up to the end again. Right? So that is all, guys. So I hope you have learned something in this video and I hope to see you guys soon. Right? See you soon.